For 2,000 years, every student, from Baghdad to Oxford, began with his words. Before Newton described motion, before Einstein bent space and time, one man gave us a universe of certainty. 2.5 millennia ago, in the bustling harbor city of Alexandria, a quiet scholar wrote a book. Not a story, not a myth, but a system of truth. His name was Euclid, and his Elements became the most influential textbook in human history. Before Newton wrote his Principia, before Descartes charted analytic geometry, before Einstein curved space-time itself, Euclid laid down the axioms, the unshakable foundations of geometry. His words shaped not just mathematics, but the very way we imagine certainty, proof, and reality. Lines, circles, triangles, simple marks on parchment, yet they contained a promise that from a few self-evident truths, the infinite complexity of the universe could be deduced. Euclid's Elements was not merely about shapes. It was about knowledge itself, and yet the man himself remains a mystery. Unlike Archimedes, no dramatic death story survives. Unlike Plato or Aristotle, no dialogues or letters, no portrait. Not even his birthplace is certain. Was he Athenian, educated in Plato's academy, or a Tyrian mathematician summoned to Egypt by Ptolemy? All we know for sure is this: Euclid flourished around 300 BC, in the reign of Ptolemy I Soter, the Macedonian general who inherited Egypt after Alexander the Great. When King Ptolemy asked Euclid if there was a shorter road to geometry than the study, Euclid replied, "There is no royal road to geometry." Alexandria was not just a city, it was an idea. Founded by Alexander, designed by Greek architects, ruled by Macedonian kings, fed by Egyptian grain, and soon home to the greatest library the world had ever seen. Here, cultures collided. Scholars from Athens, Babylon, and beyond gathered under one roof. The Mausion, the temple of the Muses. In this ferment of ideas, Euclid taught mathematics. His students were not only Greeks, but Egyptians, Babylonians, Phoenicians. He inherited the methods of Plato's academy, the logical rigor of Eudoxus, the work of Theaetetus on irrational numbers, the Pythagorean's dream of harmony through geometry. And he distilled it all into a system unlike anything seen before. Geometry had long been practical, used by Egyptian surveyors to measure fields, by sailors to chart stars, by builders to raise temples. But Euclid's genius was to strip away the dust of the Nile, the ropes of the builders, and to reveal geometry as pure thought. Shapes not as drawings, but as ideas. Proof not as persuasion, but as necessity. In Euclid's vision, mathematics became a universe of its own. Every line, every angle, every solid, defined by axioms, truths so basic they could not be doubted. And from these, through logic alone, a cosmos of theorems would unfold. And so, his life remains a riddle, but his work endures, copied by Byzantine scribes, translated by Arabic scholars, studied in medieval monasteries, printed by Renaissance humanists, and taught to every schoolchild today. No other book has had so long and so vast a life. Who was Euclid? We cannot say with certainty. Unlike Archimedes or Plato, no letters survive, no writings in his own voice. Even his birthplace is unknown. Some later writers placed him in Tyre, a Phoenician city of trade and learning. Others imagined him Athenian, shaped by the legacy of Plato's academy. In truth, history left us only shadows. To complicate matters further, there was more than one Euclid in antiquity. A philosopher of Megara, a generation earlier, also bore the name. Medieval copyists sometimes confused the two. This blur of identities only heightens the enigma. Was Euclid one man, or the leader of a small mathematical school in Alexandria whose work was later attributed to a single name? We have no direct biography. All we know is what later commentators like Proclus in the 5th century AD wrote about him. But the consistency of Elements suggests a single author of extraordinary discipline. Whether Euclid was one man or many, the system bears the mark of unified genius. Though unconfirmed, most scholars believe Euclid was trained in the Platonic tradition. In the academy, geometry was not just mathematics, it was philosophy. the pathway to eternal forms. Plato taught that geometric truths reflected the structure of reality itself. Perfect circles, infinite lines, immutable triangles. Euclid inherited this vision, but stripped it of metaphysical language. His elements would be pure logic, pure structure. Around 300 BC, Euclid emerges in history's spotlight, not in Athens but in Alexandria, the new capital of knowledge under King Ptolemy I. The Ptolemies built more than palaces. They built the Mouseion, a research institute attached to the Great Library, where thousands of scrolls were gathered from across the Mediterranean world. Here, Euclid became teacher and systematizer. He was not a lone genius working in isolation. He was part of a community, a city where Egyptian surveyors, Babylonian astronomers, and Greek philosophers mingled. Alexandria's Mouseion may have been the world's first true research university, and in its halls, Euclid taught. The fact that his works became canonical so quickly suggests he was recognized as authoritative in his own lifetime. As Alexandria grew into the intellectual capital of the Hellenistic world, Euclid's teaching became its foundation. Every mathematician who followed, Archimedes, Apollonius, Eratosthenes, began with his definitions and postulates. Geometry was no longer scattered results from Thales or Pythagoras. It was now a system, coherent and whole. And so, we arrive at his masterwork, the Elements. 13 books, 465 propositions. A cathedral of logic that would endure for more than 2,000 years. Euclid's Elements is not just a book, it is the book. Written around 300 BC in Alexandria, it has been copied, translated, and studied for over 2 millennia. More than 1,000 editions were printed after the invention of the printing press, second only to the Bible in cultural reach. But unlike Scripture, the Elements claimed no divine authority. Its power lay in something even more enduring: reason. Euclid begins not with theorems, but with foundations. He defines his objects: points, lines, circles, planes. He sets down 5 postulates, assumptions about space, and 5 common notions, self-evident rules of logic. From these, he builds an entire universe of geometry. These postulates are deceptively simple, but from them flows the entire geometry of the ancient world. The fifth, the so-called parallel postulate, would torment mathematicians for 2,000 years, and one day give birth to the geometry of Einstein's relativity. The Elements is divided into 13 books. Each unfolds like a chapter in the story of space. From simple lines to the 5 Platonic solids, the Elements is nothing less than a blueprint of the cosmos. Euclid's first proposition: construct an equilateral triangle on a given line. With just a straight edge and compass, he creates a triangle with all sides equal. It is not the triangle itself that matters, but the method. Every proposition is proved, not assumed. Book 1, Proposition 47, the Pythagorean theorem. Euclid gives the most famous proof in history. For a right-angled triangle, the square on the hypotenuse is equal to the sum of the squares on the other sides. This truth had been known to Babylonians centuries earlier, but Euclid's genius was to prove it deductively from first principles. No measurement, no experiment, only logic. Book 9 contains another jewel: the proof of infinitely many prime numbers. Euclid argues by contradiction. Suppose there are only finitely many primes. Multiply them all together, then add one. The result is not divisible by any known prime, therefore a new prime exists. And so the sequence never ends. From the mind of Euclid to the algorithms of modern cryptography, this proof echoes through millennia. Even our digital security rests on the infinity of primes. Within Euclid's constructions lies the golden ratio, a proportion that recurs in art, architecture, and nature. The Elements does not merely describe geometry. It reveals harmony, structure, and order, woven into the world itself. By the end of Book 3, Euclid presents the 5 Platonic solids, perfect polyhedra, that philosophers since Plato saw as the building blocks of the cosmos. With them, the Elements comes full circle, from point and line to the geometry of the heavens. The Elements made Euclid immortal, but it was not his only work. Ancient sources, especially Pappus of Alexandria and Proclus, attribute a constellation of other treatises to him. Together, they reveal a thinker reaching far beyond geometry, into vision, astronomy, and even the philosophy of reasoning itself. The Data is a companion to the Elements. It explores how certain given conditions, a line, an angle, a ratio, can determine unknowns. In essence, it is the study of geometric inference. You can think of data as an ancient form of algebraic analysis, where known values constrain the possibilities of unknowns. It anticipates ideas that modern mathematicians would formalize in algebra and analysis. From the notion of given comes a new way of thinking. Geometry as a system of information, not just construction. In today's terms, the Data foreshadows computational geometry and algorithmic problem-solving. Another work, the Optics, is the earliest surviving Greek treatise on perspective. Euclid assumes that visual rays travel in straight lines from the eye to the object, forming a cone of vision. This model may seem primitive, but it laid the groundwork for centuries of optical science. Euclid explains why distant objects appear smaller, why parallel lines seem to converge, why a coin viewed obliquely looks elliptical. It's not a correct theory of light. The rays don't actually come from the eye, but as a geometric model of vision, it anticipates Renaissance perspective in art and even modern computer graphics. In the Catoptrics, attributed to Euclid, he investigates reflection. The angle of incidence equals the angle of reflection, a principle still taught in physics today. From this, he derives rules for how images appear in plane and spherical mirrors. Some scholars suspect the Catoptrics may be later, but its association with Euclid shows how geometry extended into the behavior of light. The phenomena applies geometry to the heavens. Using spherical geometry, Euclid describes the rising and setting of constellations and the circles traced by stars on the celestial sphere. It's a work of applied geometry, bridging astronomy and observation. While not as famous as Hipparchus or Ptolemy's later models, Euclid's phenomena helped systematize celestial geometry. Other works are known only by title or fragments. The Porisms, a mysterious text of corollaries or propositions later admired by Pappus. The Conics, precursor to Apollonius's great work on ellipses, parabolas, and hyperbolas. The Surface Loci, exploring curves on surfaces. The Sudaria, a handbook of fallacies, teaching students how to avoid false proofs. Even an Elements of Music has been attributed to him, though its authorship is uncertain. Euclid's influence was immediate. Archimedes, only a generation younger, began his proofs on the bedrock of Euclid's axioms. Apollonius would expand the lost conics into a masterpiece of its own. Eratosthenes measured the Earth's circumference using geometric methods derived from the elements. In every corner of the Hellenistic world, Euclid's system became the lingua franca of mathematics. These works show us that Euclid was not only a geometer, he was an architect of knowledge. Whether studying light, stars, numbers, or reasoning itself, his method was the same. Begin with axioms, proceed with proof, end in certainty. From the line to the cosmos, from vision to the infinite. Euclid's horizon was boundless, yet his true legacy was only beginning. For centuries after his death, his works would vanish into silence, then re-emerge to reshape civilizations.